The question that I will be focusing on in today's talk is the following. If we fix a positive integer n and consider rational valued functions which are periodic with period capital N, then can we say that the infinite series summation f of n over n is 0 or not? Now, as you may wonder, why would one look at such a question? And when does this question even make sense? When does a series converge? So on and so forth. We will be discussing that in the talk. I will first talk about the motivation and then the history of the problem, go over some nuances of the question, and then talk about recent joint work with Professor Ramurthy, wherein we introduce what we call the Okada space and study vanishing of the special value L1F. So first, let me start with motivation. Oh yeah, and before I begin, if you have any questions, please feel free to unmute yourself and ask. Okay, so let me first talk about the motivation of this problem. The motivation to study this question comes from Dirichlet's theorem, where he proved in the 1840s that there are infinitely many primes p congruent to a modulo n when a and n are relatively prime. So this is the infinitude of primes in arithmetic progressions. This is about 100 years after Euler gave his famous proof for the infinitude of primes. So, what in Dirichlet's proof, his idea was to emulate Euler, emulate his idea, and in order to do that, he introduced what we call today Dirichlet characters. Dirichlet characters are nothing but group homomorphisms from Z mod nz star to C star, which we extend as periodic functions to the all integers by putting them to be 0 when you have integers that are not relatively prime to capital N and the character value otherwise. One character which is of interest for Dirichlet is the principal character. This is just the extension of the identity group homomorphism, and we will denote it by chi naught. Associated to each of these Dirichlet characters, which can be thought of as periodic multiplicative function on integers, we have the L series Ls chi, defined by summation n going from 1 to infinity chi of n over n to the s. This converges absolutely for real part as bigger than 1, but when chi is non-principal, one can show that this converges for real part as bigger than 0. A crucial step in the proof of Dirichlet of infinitude of primes is that the value L1 chi, or this infinite series chi of n over n, is non-zero for any non-principal character chi. He needs this in order to show that the pole coming from the principal character, the L series of the principal character, does not go away. And so one can do something similar to what Euler did and hence conclude infinitude of primes. So it is important from an arithmetic perspective that we show the non-vanishing of this infinite series. One may ask, okay, how does one go about proving this? There are several proofs of this fact known. Typically, one splits this proof into two cases, one of the complex characters and one of the real characters. In case of the complex characters, because chi and chi bar are distinct characters, if L1 chi is 0, then L1 chi bar is 0. And so if we look at the product of all Ls chi's, chi mod n, then that will have a 0 at s is equal to 1. And hence, as you take the limit as s goes to 1 of this particular product, you will approach 0. One can show that that is a contradiction by looking at the Dirichlet series of this product and seeing that it is positive for s bigger than 1. In the case of real characters, that case requires a little more work. One can go several ways. Two ways that strike to me are one being the algebraic number theoretic way, which is the Dirichlet class number formula. In this way, we connect the value of L1 chi d to the class number of the corresponding quadratic field 8 sub d. And because the class number is non-zero, one gets that L1 chi d is non-zero. Another way of going about it is using Landau's theorem on Dirichlet series with non-negative coefficients that they have a singularity at the abscissa of convergence. Using these ideas, one can show that L1 chi is not zero. But the point to note here is that these proofs rely heavily on the fact that these Dirichlet characters are multiplicative functions and that they have nice algebraic structure associated to them. But one may wonder, is that really necessary in order to conclude non-vanishing? Is it really necessary for the functions to be so structured and restrictive? This was the motivation behind Chowla's problem, where in 1964 he asked, can one conclude a similar kind of non-vanishing result for general periodic functions? In particular, he posed the following problem. He said, suppose you take a rational valued function periodic with a prime period p, satisfying two conditions. One, f of p is 0, and the other is that summation of values of f over all residue classes mod p is 0. Then is it true that this infinite series, summation n going from 1 to infinity, f of n over n is not 0? He was able to prove this in the case when f is an odd function. By odd function, I would mean that f of negative n is minus f of n. In that situation, using an argument outlined by Siegel, Chowla was able to show that this is indeed the case. However, in the general situation, this question was still open until in 1974, Baker, Birch, and Wirsing proved a general result from which one can conclude an affirmative answer to Chowla's problem. In particular, they showed that if you look at an algebraic valued periodic function, periodic modulo any integer capital N, not necessarily prime, satisfying two conditions. One condition is on the support of f, namely that f is supported on non-zero co-prime residue classes mod q, as well as the zeroth residue class. So that's the first condition. One that I've said over here. And the condition 2 is on the values of the function. That is, the values that f takes should be disjoint from the nth cyclotomic field. Under these two conditions, they showed that the series summation n going from 1 to infinity f of n over n is non-zero whenever it converges. So in this theorem of Baker-Birch and Wirsing, if we take capital N to be prime, then and the function to be rational valued, then both condition 1 and 2 are satisfied, and hence we get an answer to Chowla's problem. The method that Baker-Birch and Wirsing used was heavily relied on Baker's theorem of linear form in logarithms, and we will come to that in a few minutes. All right. So in the same paper where Baker-Birch and Wirsing gave this characterization of non-vanishing, they also gave examples showing that the conditions 1 and 2 are really necessary in order to conclude non-vanishing. In particular, they gave examples where if the function did not satisfy 1 or 2, then you do get examples such that the series that in question actually vanishes. Since the examples are quite nice, I thought I would include them here. For the first condition, wherein the first condition was on the support of the function f, if we do not insist the condition on the support, then it is not difficult to construct functions such that L1f is 0. In particular, one can construct this function, which is just 1 minus p over p to the s squared times zeta s. Because zeta has a pole at s is equal to 1, one of the Euler factors will cancel the pole, and the second Euler factor will introduce a 0, giving us that the summation n going from 1 to infinity f of n over n is equal to 0. And the fact that this corresponding function does not satisfy 1 is noticed by the fact that it is supported on this prime class as well. What about the second condition? So the second condition was on the field of values of the function. The second condition said that f needs to take values disjoint from the nth cyclotomic field. If we relax this, then again, one can find examples of functions such that the series vanishes. The example that Baker-Birch and Wirsing give are of characters chi and chi prime mod 12 with conductors 3 and 4. Because they are odd characters, their L1 chi values will be algebraic multiples of pi, and then correspondingly, if one can adjust the values so that we get that the series vanishes. Right. So we see that relaxing any of the conditions in the Baker-Birch-Wirsing theorem would give us many examples such that the series f of n over n does vanish. So we can, instead of asking when the series is zero or not, one can change our approach and ask the question of whether we can classify all functions such that the series is zero. In other words, can I classify all f such that they say either do not satisfy condition 1 or do not satisfy condition 2, and for which this particular series is zero. In this talk, I would like to focus on examples of this type, examples of the type 1, where the values of the functions are disjoint from the nth cyclotomic field, but we don't emphasize the support condition. So f can be supported on any residue classes mod capital N, but we insist that the values that f takes are rational, for instance. Just for simplicity, let's stick to rational. So this is the motivation, this is the focus of the talk. One motivation behind considering this problem and focusing on it is this innocent looking conjecture of Erdish.
Sorry, Siddhi, before you go on, could you show me the condition 2 again, please?
Yes.
So it's a disjointness with I see, with the roots of unity corresponding to the period, is it?
That's right. Yeah, yeah.
And in your second example, what happened here? You have two characters taking
the characters were mod 12.
Yeah.
So we would have square root 3 inside q zeta 12. And so if I'm insisting that f is 2 times chi minus square root 3 times chi prime, then although it is supported on coprime residue classes, it will have values in the cyclotomic field. And then I can adjust it so that the series becomes zero.
Okay, thank you.
Mm-hmm. All right. So as I said, we will be focusing on trying to classify all functions for which are not necessarily supported on coprime residue classes. So the support of the function can be any residue classes, but the values that they take are rational. And the motivating problem behind focusing on this case is the following innocent looking conjecture of Erdish. So in 1965, Livingston was trying to attempt Chowla's problem. And in doing so, he wrote to Erdish about the problem. So in written communication with Livingston, Erdish claimed the following statement. He said that suppose I look at a function on the integers, which is periodic mod capital N, say, such that on all the non-zero residue classes mod n, the function takes plus minus 1 values randomly, any plus minus 1 values. But at the zero residue class or at the multiples of capital N, the function takes 0. So it's a bunch of plus minus 1s and then 0, bunch of plus minus 1s and 0, and so on. Then if you look at the corresponding infinite series, summation n going from 1 to infinity f of n over n, that is not 0. Whenever the series converges. Of course, one has the convergence condition, but whenever the series converges, this particular, in this case, we would have this series to be non-zero. Now, this does not satisfy the Baker-Birch-Wirsing condition 1 because the support of the function is all non-zero residue classes, but it does satisfy condition 2 because the values of the functions are plus minus 1s. So they are disjoint from all cyclotomic fields. When does this series converge? We will see in a few minutes that in order for this series to converge, a necessary and sufficient condition is that the sum of values over all residue classes is 0. And so in this case, the convergence condition will force that capital N be odd because you're insisting that f of capital N is 0. So up to n minus 1, you want equal number of plus minus 1s. So n minus 1 should be even, that is n is odd. What do we know about this conjecture? If you look at capital N to be prime and look at Baker-Birch-Wirsing theorem, then in that case, F is supported on coprime residue classes and takes values disjoint from the sixth atomic field. So the Baker-Birch-Wirsing theorem would immediately imply Erdish's conjecture when capital N is prime. The other case, important case which is known, is when capital N is 3 mod 4. When capital N is 3 mod 4, Ramurthy and Sarda in 2010 showed that Erdish conjecture holds. That is, in particular, the series is not zero. As a part of my thesis, I was able to show that this Erdish conjecture holds for 100% of Erdish functions. So in a probability sense, this conjecture should hold with probability 1. The case that I have not talked about is when n is congruent to 1 mod 4, and in that case, this conjecture is open. So we do know some special conditions, like we know the conjecture when capital N is a prime power, or when capital N is a product of two primes, and some other special cases. But the general case when N is congruent to 1 mod 4 remains open. And so one would like to understand what really goes into this conjecture. Why is the case n congruent to 1 mod 4 still unresolved? With that motivation, we are going to try and classify all functions such that they are rational valued, supported on any residue class as mod n, and for which the series is 0. That is our goal. So first, let me describe the setup that we are going to look at. So in order to discuss such questions, it is convenient to associate an L series to them, like we attach an L series to Dirichlet character. So let's attach an L series to the periodic function f as f of n over n to the s. It will absolutely converge for real part as bigger than 1. What one can do for real part as bigger than 1 is then group together terms corresponding to the same residue class. Once we do that and we take a common factor of 1 over n to the s, then what remains inside is precisely the Hurwitz zeta function. So these functions over here that show up are the Hurwitz zeta functions. The Hurwitz zeta function is nothing but a shift of the Riemann zeta function. And the analytic properties of the Hurwitz zeta function are quite well studied. In particular, it is known that the Hurwitz zeta function has an analytic continuation to the complex plane except for a simple pole at s is equal to 1. Putting that in here, we get that LSF has an analytic continuation to the entire complex plane except for a simple pole at s is equal to 1. And then the residue can be computed immediately. Thus, in particular, if I want to study the value L1F, then it is necessary and sufficient that the residue vanishes, and one can show that the value is equal to the series f of n over n. And so the convergence condition becomes that summation a going from 1 to n f of a is 0. So henceforth, whenever I talk about the value at 1 of this L series, I will assume the convergence condition. I will assume that f satisfies this particular condition. Okay, so when f satisfies this condition, what exactly can we say about the value at 1? We can say the following. So here I have written again LSF in terms of the linear combination of the Hurwitz zeta function. As we take limit s goes to 1 from the right, the Hurwitz zeta function behaves like 1 over s minus 1 minus psi of x plus big O of s minus 1. The psi of x is nothing but the logarithmic derivative of the gamma function. We call it the di-gamma function. And so once we substitute this back in over here, we can rewrite the value L1f as a linear combination of the di-gamma values. So L1f is nothing but summation f of a psi of a over n. What this tells us is that when L1f is 0, we would get a linear relation among these di-gamma values. So another interpretation of the fact of the study of L1f being 0 or not is studying whether there are any linear relations among these values or not. Another interpretation which becomes essential for our study is through the Fourier transform. So because f can be interpreted as a function on z mod nz, where you have a discrete Fourier transform, we can use that Fourier transform in the series to get another expression for L1f in terms of the log of these cyclotomic numbers. So L1f is nothing but summation b going from 1 to capital N minus 1, f hat of b, log of 1 minus these cyclotomic numbers. These cyclotomic numbers, for when n is not a prime power, will become units. And so the study of L1f being 0 can be interpreted as a study of multiplicative relations among these cyclotomic units. So here you have various interpretations of this study of L1f being 0 or not. Because you have the log of these algebraic numbers showing up, it is not surprising that Baker's theorem becomes relevant to this problem. In 1967, Baker proved this following theorem, for which he received the Fields Medal. It was a breakthrough result in transcendental number theory. He showed that if you have algebraic numbers whose logs are q-linearly independent, that means the logs do not satisfy any trivial relation, then the logs are q-bar linearly independent together with 1. So any non-zero linear form in log of algebraic numbers will be transcendental because of the one that is showing up here. Using this Baker's theorem, Baker-Birch-Wirsing were able to show that L1f is not 0 if f is supported on co-prime residue classes and takes values disjoint from the capital N cyclotomic field. Because it highlights the nuances of their techniques, I have quickly outlined a proof here. In the interest of time, I won't go over all the steps, but just indicate the main things. Because we would like q linear independence among the logs, we first choose a maximal q linearly independent subset of these log of cyclotomic numbers and write everything in terms of these. Then L1f being 0, using Baker's theorem, transforms that question to a question of relations among the Fourier transform of the function. Now, the Fourier transform, if you write out the definition, is interaction between values of the function and the cyclotomic and the roots of unity, the capital and its roots of unity. And so heuristically, if you don't want such calculations to happen, we would like f to be disjoint from the nth roots of unity, and you would somehow want the nth roots of unity to be primitive. You don't want any contributions from the lower levels to be coming. These are the two heuristic reasons why one expects the two conditions in the Baker-Birch-Wirsing theorem. Their idea then is that now that everything is converted to an algebraic setup, one can apply Galois automorphisms to this relation. And using Galois automorphisms from one function whose L1f is 0, one can produce phi of n many functions whose L1f is 0. And then because f is supported on co-prime residue classes, one can use some linear algebra techniques to conclude that f has to be identically 0 if this is the case. So this was a brief sketch of the techniques that go into the Baker-Birch-Wirsing theorem. But now coming back to our problem, the problem was, can I classify all rational valued functions f modulo capital N such that the value at 1 vanishes? This question was first considered by Okada in 1982. In 1982, what Okada did was obtain a vanishing criterion for such functions. So in particular, what he said was that as long as the function values are disjoint from the capital N cyclotomic field, one can give a linear algebraic view of whenever L1f is 0. So he said that L1f exists and equals 0 if and only if you look at the, if you look at the vector f of 1, f of 2 through f of n, then that should be a solution of these phi of n plus omega of n many linear equations. So there is one equation for each coprime residue class mod n, and there is one equation for each prime divisor of capital N. For so these will be phi of n many equations, and these will be omega of n many equations, where omega denotes the number of distinct prime divisors of n. Here, the numbers AANs and epsilon APs can be explicitly given. These are explicit rational numbers, which can be given in terms of the arithmetic information of capital N. I have written out the definition here, but it really, for now, we can just concentrate on the fact that AAN is a rational number coming from, depending on the GCD that A has with capital N and the prime factors of capital N and N over T. Epsilon APs, again, depend on the arithmetic of capital N and capital A. So here VP of A is just the order to which P divides A. Using these kind of numbers, he showed that for L1F to be 0, it's sufficient that f of 1 through f of n satisfies these linear equations. So the question now of whether the series is 0 or not transforms to a linear algebra question of when can a function f of 1 through f of n satisfy these conditions. Because of the messy nature of the definition of these numbers, because these AANs and epsilon APs are so defined in such a convoluted way, Okada's theorem for a long time was only looked at from a linear algebra perspective. And really, it doesn't seem from here that one can verify whether plus minus ones are a solution of the system or not. So it was more or less not paid attention to from an arithmetic perspective. But what one can conclude from here is my joint work with Professor Murty. One thing that I would like to remark before I move ahead is that the convergence condition, that is summation f of a being 0, is included in the span of the Okada relations. So although it is not obvious from these relations, while proving them, one includes the relation that summation a going from 1 to n is 0. And so when we look at the dimension perspective, then the dimension of f such that L1f is 0 would be capital N minus phi n minus omega of n, because those are the linear equations that we are putting on these variables. Okay, so we don't have to worry about the convergence condition. But what more can we deduce from Okada's theorem? So in joint work with Professor Ramurthy, what we do is we introduce these vector spaces. The first space f of n is just all rational valued functions mod n. F0 of n will denote those rational valued functions for which L1f exists, and O of n will denote those functions in particular for which L1f equals 0. This space we will call Okada space, and our aim is to understand the Okada space in more detail. Can we understand the structure of the Okada space? Towards that, what we do is we construct an explicit basis using Okada's theorem. First of all, the Okada's theorem, as I said, would mean that the dimension of the Okada space is n minus phi n minus omega of n. If I put capital N to be prime, then this dimension is 0, proving Chowla's theorem again, that for capital N prime, there are no functions for which this value L1f equals 0, or this value vanishes. Okay. So using Okada's theorem, what we do is we construct an explicit basis for the space. We construct a basis which you can use very easily. Using this explicit basis, an immediate consequence becomes extensions of the theorem of Baker-Birch-Wirsing. We get extensions of the earlier work of Murty and Saradha on values of the digamma function and their linear independence. Another thing that immediately follows is a variant of the Erdish conjecture, which I will talk about in a few minutes. Apart from this, these direct consequences of this constructing the explicit basis, we highlight the fact that the numbers AAN, which appear in the Okada's system of equation, are very important. In fact, these are the numbers that will hold key in order to understand Erdish conjecture or any such kind of conjectures. So the numbers that were so far kind of pulled under the rug and just said that they were rational numbers, it actually turns out that their arithmetic is what will play an important role. So that is something that we highlight and we study these numbers. The last thing that I would probably talk about today would be that these kind of questions are connected to the arithmetic nature, the transcendental nature of Euler's constant gamma. This Euler's constant is nothing but the value of psi of 1 minus psi of 1, the digamma function at 1. And so I will briefly talk about how these kind of questions connect to the arithmetic nature of Euler's constant. Since I might not have time to go through all of these extensions, I will probably only indicate how to go through some of them as we move along. But before I do that, are there any questions?
No, it looks very good. Thank you.
Thank you. So as I said, the Okada space was the space of functions for which L1f is 0. And this is the space for which we want to construct an explicit basis. So let me recall the Okada relations once again. Here I have written them in the form that Okada had written. So you have the variables x sub n's plus xa, aans, and x capital N over phi of n is 0. So we have phi of n many such relations and omega of n many relations corresponding to every prime. What we noticed here is that this phi of n is nothing but 1 over phi of n is nothing but a of capital N comma n, so that we can include the last term in the summation over here itself. And we notice that these numbers are 0 if p does not divide the number a. If p does not divide the residue class a, then these numbers will be 0. Using these two observations, the system now becomes the following. So here I have just included the capital N residue class in the summation. And in the second case, I have only kept those terms for which epsilon AP is non-zero and then divided by the coefficient of x sub p, which was epsilon pp. Why I did that, the reason will be clear in a minute. But before that, notice that in these equations over here, when I look at a particular coprime residue class n, then only x sub n shows up and no other x sub m for m coprime to n will show up. So only one of the the coprime residue classes will show up in this case. Similarly, if I focus on the equations corresponding to the prime divisors, only the prime divisor p would show up and no other prime divisor, no variable corresponding to the other prime divisors show up in this equation. So we see that the coprime residue classes, which are over here, and the prime divisors of residue classes, which are here, these are the ones on which we have certain restrictions. Whereas the classes that are not coprime or prime, they don't seem to have any restrictions put on them. So we call a class, a residue class A mod n, to be free if it is neither coprime nor prime. Now what we do is we order all the residue classes. So remember, in Okada's system, we had the vector f of 1, f of 2, all the way up through f of n. What we do is we reorder these residue classes as first the co-prime residue classes, the prime residue classes, and then the free residue classes in the increasing order amongst each of the category. So first we have all the co-prime residue classes, then I write down all the prime residue classes, and then the free ones. Okay, why do we do that? If we do that, then what happens is this system of equations star can be written in a matrix form, and the matrix turns out to have a very nice structure. So because in the co-prime case only the co-prime associated to that particular relation shows up, and similarly in the prime case only the prime associated to that relation shows up, the matrix of these system of equations has the following reduced row echelon form. So here I've tried to kind of sketch how the matrix looks like to give a visual idea. Because you have co-prime associated to co-prime, you just have a bunch of ones on the diagonal, and all the other non-zero coefficients will occur otherwise. And then you'll have these prime ones, just ones on the diagonal, and then the free residue classes, and then no relations for the free residue classes, so bunch of zeros. Okay, now I've reduced the question to a basic linear algebra 101 problem. So in order to determine a basis for the Okada space, all I need to do is find a basis for the null space of this matrix. And that is easy, right? We just take take the function that is 1 on one of the free residue classes and 0 on the other free residue classes, and then work backwards. So do a back substitution method. So that's what we do. In order to construct this explicit basis, we take the functions e sub r's. These e sub r's are functions mod n that are, let's say, 1 on the residue class r mod n and 0 on any other free residue class b mod n. So we'll get a 1 here, and then e sub r of p and e sub r of n can be worked out by just going through these equations one by one, just going through the back substitution method. Using that and keeping track of the coefficients, one gets the following theorem. So these functions e sub r, as r varies over the free residue classes, form a basis for the Okada space. They can be written down explicitly. So for the free residue classes, as I said, they look like the standard basis. For the prime residue classes, we see that there are two cases. One, if p squared divides capital N, and the other if p exactly divides capital N. These are just these numbers, epsilon APs and epsilon PPs. So ER of P's in both the cases is given very easily. Here, this condition V sub P of R being greater than or equal to V sub P of N means that the free residue class R is divisible by a higher power of P than that at N. Okay, and what about the co-prime residue classes? Well, at the co-prime residue classes again, one can write this ER of N as minus ARN minus P divides N, ER of P, APN. Here ARN and APN were as in Okada's system of equations. And yes, that is the basis. One nice thing about this basis is that it is like the standard basis on the free residue classes. And so if I have any f in the Okada space, then the expression of f in terms of the basis is immediate. One can simply write f of n as summation over r free f of r times er of n. As a consequence of this simple and explicit basis, we get some nice corollaries. First is the extension of the Baker-Birch-Wirsing theorem. So in the Baker-Birch-Wirsing theorem, one had to restrict oneself to only the support being co-prime residue classes. But because of this basis, we see that not only the co-prime residue classes, but one can let F be supported on also the prime residue classes. As long as F is 0 on the free residue classes, L1F is 0 only if F is identically 0. So we can let the support of F be extended to also the prime residue classes.
Can you remind us what F0 of n is?
Oh, that is simply the set of all periodic functions for which L1F exists. Yeah, so they are the periodic functions that satisfy the convergence conditions. So I can talk about L1F. In the Baker-Birch-Wirsing theorem, we also allowed for the zero residue class. We also allowed the support of F to contain the zero residue class. So here what we can say is that if the support of F is on the co-prime, prime residue classes and the zeroth residue class, then L1F is 0 if and only if F is a rational multiple of the vector E sub capital N. And E sub capital N can be explicitly written down, as I just mentioned earlier. So this gives us a way to extend all the previous linear independence results of digamma values that used Baker-Birch-Wirsing theorem. So instead of using Baker-Birch-Wirsing, we could now use this extension and get generalizations of all those results. Another consequence of getting this explicit basis is that we can study a variant of Erdish's conjecture. The motivation behind studying this variant is that recently it was found by Tengli using some exhaustive computer search that you can find a function which is periodic mod 36 that has values in plus minus ones for all n. So this differs from the usual Erdish conjecture because the usual Erdish conjecture insists that on zero residue class it takes the value 0, whereas this function is plus minus 1 on all residue classes. So he found a function mod 36 such that it satisfies this plus minus 1 condition and has L1F equals 0. So the value at 1 vanishes, and via his computer search, he was able to show that 36 should be the smallest such n for which such a function exists. So then this begs the question of understanding this from a more theoretical point of view. Can one classify capital N such that there exist functions such as these, that plus minus 1 on all residue classes and L1F is equal to 0? So one can study this problem in its own right. It's interesting by itself. The point to note here is that the convergence condition, remember the convergence condition was that the sum of values of F on all residue classes should be 0. Because F is plus minus 1, this forces that in order to talk about L1F, capital N must be even. So we now focus on even ends as opposed to odd ends for Erdish conjecture. In even ends, when can you show that such a relation exists or does not exist? We are able to prove one case of this particular variant, namely that when capital N is 2 mod 4, then such a relation does not exist. That is, you do not have any F with plus minus 1s in the Okada space such that L1F is 0. Okay, since the proof is quite straightforward, let me immediately give that to you. Suppose we had such a function in the Okada space. Suppose we had a plus minus 1 function whose L1F is equals 0. Then I can write it in terms of the basis E sub r. So I can write f of n to be f of r er of n. In particular, I focus my attention at n is equal to 2. So I get that f of 2 is f of r er of 2. Now, because n is 2 mod 4, 2 divides n exactly. Because 2 divides n exactly, the value er of n is very simple. Let me show you what the value er of n was. So we are in this situation that p exactly divides capital N. Then er of p is minus 1 if p divides r and 0 otherwise. So this is a very simple case. Using the fact that er of 2 is supported only when 2 divides r, we get that f of 2 is minus summation f of r, where 2 divides r and r is free. Now the number of terms on the right hand side are multiples of 2 except 2. So the number of multiples of 2 up to capital N will be n over 2, but we are removing the prime residue class. So we are removing 2, so minus 1. Because n is 2 mod 4, n over 2 is odd, minus 1, which is also odd. So the number of terms on the right hand side is odd. Each of the term is non-zero, hence the right hand side would be even. So we get that the right hand side is even. But f of 2 is plus minus 1, so f of 2 is odd, giving us a contradiction and immediately telling us that when n is congruent to 2 mod 4, we cannot expect such a relation to hold. So one kind of gets one case of the variant of Erdish conjecture. This proof will fail when n is congruent to 0 mod 4. When n is congruent to 0 mod 4, one has to look at the co-prime residue classes. One cannot simply look at the prime residue classes. And so the arithmetic of these numbers ARN comes into picture. So that becomes important. And another point to note here is that the proof for Erdish conjecture when n is 3 mod 4, a similar proof can also be given in this case when n is 2 mod 4, the idea being looking at the ideal generated by 2 in the cyclotomic field and looking at the equations mod that. But a similar, there seem to be parallels among the Erdish conjecture and the variant of Erdish conjecture. Because of these parallels, one may ask, since we have a counterexample for the variant, do we also have a counterexample for the Erdish conjecture? Maybe, maybe not. So that is an interesting problem to pursue in its own right. Since I am close to time, let me simply say that these ARNs, the numbers at ARNs, they depend a lot on the arithmetic of capital N. And it would be nice to understand exactly how these rational numbers look like. In fact, one would like to understand how their denominators look like, get a handle on their denominators. That seems to be a hard question for now, but what we are able to do is we are able to get different expressions for these numbers in terms of characters, Dirichlet characters modulo n over t. And using this expression, one can find out what these numbers are in certain special cases and get a good bound on these numbers. So here we are highlighting that the arithmetic study of these rational numbers should be important as well. The last thing that I had mentioned was relation to Euler's constant. And what one can do is one can study the spaces spanned by the digamma values and the subspace of that spanned by the values L1F. And it turns out to be an important question whether this containment is strict or not. So it depends on our considerations whether this containment is strict or not depends on whether gamma is a Baker period or not. Because it's not difficult to show that the span of the digamma values is the span of L1F plus rational multiple of gamma. And we expect this to be a direct sum. We expect that gamma is not a Baker period, and so this sum of vector spaces is direct. However, that seems to be a hard problem. What we are able to show is that there can be at most one exception. That is, if the equality happens for some n, then it does not happen for any other m which is co-prime to capital N. And the method would be to show that if you have two periodic functions mod n and m, then they cannot be equal if n and m are relatively prime. Okay, I think I'll stop here because of the time constraint. So in conclusion, I would like to say that our investigation is basically just a beginning into approaching these problems from the point of view of structure of the Okada space. And hopefully this will lead to further insights into the problem. Thank you.
Very good. Thank you. I think there's an icon way of doing this, which let me see. Yeah. Okay. That's very nice talk, very clear, well explained. Siddhi, thank you very much for that. Are there any questions people would like to ask? I can't see everybody, so I think you can just either raise your hand or just speak up. Okay, while we're waiting for people, maybe I'll ask a few questions. So it still leaves open the original conjecture for N1 mod 4, is that right?
Yes, it seems that for N1 mod 4, one would really need to understand denominators of these numbers, ARNs. Yeah.
I see.
Yes.
And what happens if we weaken this whole thing to or make a bigger, larger class where you allow algebraic values of f instead of rational values? Is that at all approachable?
So for algebraic values, because in the co-prime case itself, one may have cancellations. That's why I think it is tricky to approach the algebraic values. But I think one may still get somewhere by restricting to odd functions versus even functions. So as in the Baker examples, as we see, the example was for odd functions. If we restrict to even functions, then there should seem to be much fewer relations amongst them because of the Baker periods. So if we restrict ourselves to even functions, then perhaps one can still study these for algebraic valued. In odd functions, there are these too many cancellations, so I guess it would.
And when you're looking at rational values, these are essentially integer values, right? Because if you multiply any of these functions by a denominator, they still satisfy the same conditions, don't they?
That's right. But as a vector space, I guess it's over Q. And these ERNs, though, would be Q valued because of the ARNs, which are rational numbers. So in fact, it would be a very it would be very nice if we get a rational basis, an integer basis for the Okada space as opposed to a rational basis. Then these questions of denominators would not haunt us.
I suspect you can do that. We have to think a little bit more about that. Good.
Yeah.